This is chapter 2, Switching Concepts. There are two main sessions in this chapter. 2.1, the frame forwarding, and 2.2, switching domains. The third session just a summary. So let's begin. 2.1, frame forwarding. Layers. We already learned this in CCNA 1 course. There are 7 layers for OSI model, where OSI stands for the Open System Interconnect model. It's a great model for learning, but for more practical, we prefer to use another model, that's the TCP/IP model. But refer to here, let's go over the OSI model. The bottom layer is the physical layer. In this layer, we mainly focus on the hardware. The binary data is transferred between the hardware and also the signals and so on. And then let's move to the second layer, the data link layer of the OSI model. It provides reliable transmission of the frames between the devices. So the keywords are between the devices, MAC addresses. So there is no network transmission in this layer. The third layer is the network layer. In this layer, we start talking or focus on the data transferred between networks. And here, mainly using the IP addresses. So the keywords are between the networks, also IP addresses. The next layer, layer 4, is the transport layer. For the transport layer of the OSI model, it ensures the end-to-end communication. Also make sure the transmission and the communication between the devices in the network or in the system is reliable. The data flow control between the two devices on different networks. The next layer, layer 5, is the session layer. This controls and the synchronization, maintenance, and the termination of communication sessions between two devices. Layer 6 is the presentation layer. This layer mainly handles the data translation, the presentation for the data to the user, including encryption, compression to ensure the data is in a form or in the format both the sender and the receiver can understand. And then the last layer, layer 7, this is the application layer of the model. It provides the direct interface and the end user services. It facilitates communication between the software application and also the low-level network services. So here is a quick review for the layer 2 devices, such as switch. Switch can be the number 1, is the most commonly used layer 2 devices. And then we have bridges. As you can see, this is the symbol for bridge. Most members know the symbol for switch, but may not know the bridge. Bridge is an old device, and the function is mainly and the bridge was used to divide larger network into smaller segments and reduce collisions. So the main purpose is to reduce collisions. But now for our switches, they can do the same job and more. And then we talk about the NIC, where NIC stands for the Network Interface Card. So every device that need to connect to network, including the local network or the internet, requires having a NIC. So a NIC connect to a cable or a NIC supports Wi-Fi. The card operates at the layer 2 level, providing the necessary hardware interface between the device and the network medium. And then now we have the Ethernet. This is the most common protocol used at layer 2. Ethernet frames contain MAC addresses, and these MAC addresses are for the source and the destination devices. We have virtual LAN, where virtual LAN, also called VLAN, is a layer 2 technology. We're going to spend more time on it. So for now, we know virtual line just a way to categorize or grouping our devices virtually without reconnecting all the devices. In other words, once we connect all the devices into the switch, we can simply group them virtually using commands or even software to group them. Certain devices are in certain groups, and the devices in a group can or cannot be or related to a device in a separate group. Of course, we can make them communicate. And then we're gonna learn spanning tree protocol. This is a very useful protocol. It is enabled by all Cisco devices by default. This is preventing some packets loop in the system forever, and then our system, especially the CPU of the device, will quickly overheat it and shut down. We're going to learn this in the later chapter. Frame relay, ATM, which stands for the asynchronous transfer mode, HDLC, high-level data link control, they will be introduced in remaining chapters. And then we have the layer 3 devices. The number one we're going to talk about, for sure, we all know it, that's the router. Since this is the device, make connection between networks, so that must be the layer 3, the network layer. So this is the most commonly used layer 3 device. They are responsible for forwarding the packets based on the IP address. We don't use MAC address anymore. MAC belong to layer 2, and the IP related to network using in layer 3, the network layer. Routers can make decision on where to send the packets based on the destination IP address and their routing table. We're going to spend more time on this in the upcoming chapters. And then we have the layer 3 switches, also called the multi-layer switches. These are more advanced switches, way more powerful, of course, more expensive than the conventional switches, the one we referred to in the past. And this is the switch, or the special switch can act like a switch and a router. In other words, it's a combination of router and a switch. And then we have the routing protocols. These are the protocols used by routers to determine the best path for a packet to reach its destination. The example includes RIP, the Routing Information Protocol, OSPF. Make sure you know this, start remembering this acronym, and that's called the Open Shortest Path First. We're going to encounter this many times in this and the next classes. There will be questions in the CCNA exams related to OSPF, the Open Shortest Path First. And then we have the EIGRP, Enhanced Interior Gateway Routing Protocol, and also the BGP, Border Gateway Protocol. And then, of course, we have the IP, Internet Protocol. We have the ICMP, Internet Control Message Protocol. This ICMP is used by network devices like routers to send error messages and the operational information. So now let's talk about the differences between TCP and IP, because we need this information later. The full name for TCP is Transmission Control Protocol. And then the complete name for IP is the Internet Protocol. The purpose for TCP is responsible for providing reliable and ordered data delivery between the devices in the IP network. So the keywords are reliable, also ordered data. So when the data being transmitted in the system in the network, they will be partitioned into smaller pieces at a time is being delivered and received to the destination. Based on the order of each piece, we have to assemble them together. We cannot put the pieces in random or different orders. Otherwise, the data won't be recognized. So we have to reconstruct the data in certain order, in the order it was disassembled. And the IP is responsible for addressing and routing packets of data that can be sent across the network and reach their intended destinations. It defines how data packets are encapsulated, addressed, and also routed. The functionality for TCP is it manages establishment, maintenance, and the termination of connection between the devices. For IP, mainly for handling the routing of the data packets. It also determines how to get the data from the source to the destination. In other words, when the packets transfer from one device to the other device in different networks, mainly, we use the IP to locate destination device. TCP is very reliable. It's more reliable than IP. And for IP, of course, is less reliable than TCP. So the keywords here is the best effort delivery. It tries its best to deliver, but it won't guarantee. So certain packets might be lost due to any reasons for transmission. That is okay in this case. Of course, as the recipient might recognize the data lost. For example, if there's a voice over IP, the internet phone, the recipient may hear the voice is not clear because there's some packets lost due to transmission. But there's a tolerance, or most likely we can tolerate that. The worst case scenario is to talk again, to repeat the conversation, or we hang up and call again. And then for the header information, the TCP header contains information such as source and the destination port numbers, the sequence, and also acknowledgement numbers, the control flags, which is ACK, CYN, FIN, and so on, and the window size for flow control. For IP header contains information such as the source, and the destination IP addresses, protocol version, IPv4 or IPv6, and also time to live, TTL. This is important. We're going to spend more time on this, and the other control information for routings. So this is a review session. Here shows the Ethernet frame. The whole horizontal row, that is the frame. The frame header is on the first field. If you break it down, or if you look closer, there are subframes. The first subframe inside the frame header is the preamble, and then followed by destination MAC address, source MAC address, and also the type. The purpose for this Ethernet frame is to encapsulate and transport data packets over the Ethernet network, provide a standard structure that includes the source and the destination MAC addresses, as we mentioned earlier, inside the subframe. The type and the length information, the actual data payload, the error checking information. This structure allows the devices on the network to correctly interpret, forward, and deliver the contained data to the appropriate receipt. The preamble in a frame header serves as a synchronization signal. This can help receiving device detect the start of the data frame, so it knows where to start. You won't pick a random place and start to dissect. So you know the starting point, and from there start to dissect the data. In other words, it's de-encapsulated data. The preamble is a sequence of alternating zeros and ones that prepares the receiving device clock and the circuitry for receiving the incoming data frame. It also helps the receiving device establish bit synchronization with the incoming signal. Here, we talk about the physical address of the recipient device. This is the MAC address of the recipient's device, and then followed by the MAC address of the sender's device. Here, I put the slide in the dark pink color, which means it's reading assignment. Please read. And then now we are going to review two keywords because we'll use these two keywords in the upcoming sessions. There are two terms are associated with the frame, either entering or leaving an interface. Ingress, which means the data, the signal entering into an interface, and egress means the data or signal leaving that interface. A switch forwards based on the ingress interface and the destination MAC address. A switch uses its MAC address table to make sure forwarding decision. The picture represents a switch interface. There are interface 1, 2, all the way to 6 in this case. The actual switch contains way more interfaces. And then the table on the right is the port table, also the routing table. So as you can see for port 1, currently the destination address is called an EE. Port 2, the destination address is AA. So the data will go to EE in port 1. For data in port 2, it will go to AA. A switch will never allow traffic to be forwarded out the interface it received the traffic, which means it won't return to the sender directly. The sender sends the signal to the interface receives it, it only can go to other places, it won't go back to it. So here, the addressing learning, also the MAC learning example. As you can see in the center, we have a switch. It's called the WAN switch 1. And then computer A with this MAC address, AAAA.AAAA.1111. And then for computer B, and then they connect to different interfaces. Computer A connects to port number 3, and then computer B connects to port number 2. And then if you look at the MAC address table on the top right corner, we can see the computer A MAC address is being recorded into the table, and that is associated to port 3. And then the cloud here shows it recognizes, right? It recognizes the computer B. That's BBBB.BBBB.2222, the MAC address of it, is connected to port 2. I better record that in the MAC address table. So the switch learn computer B is connected to it, and is going to record this information to its MAC address table. This table is only usable or is only there if this system is running. If you power this down, we will lose the data. In other words, this is stored in the volatile memory, in the RAM. And here, using the command called show MAC address, make sure there's a hyphen table. So the show MAC address hyphen table command, we will retrieve the MAC address table. In this example, we see these devices are connected to our switch differently in different ways, either static, connect directly. Those devices have static IP assigned, and then we have other devices connect to the same switch, but dynamically. So the switch learn and also forward method. The switch uses a two-step process to learn and forward packets. Step 1, learn. So examine the source address and add the source MAC if it's not in the table, and reset the timeout setting back to 5 minutes if the source is in the table. In other words, by default, the switch will learn the connectivity every 5 minutes. Step 2, forward, examines the destination address. If the destination MAC address is in the MAC address table, it is forwarded out to the specific port associated with it. If the destination MAC address is not in the table, here you just need to flood it out to all interfaces except the one that was receiving the data. In other words, it flood out the data to all the ports except the port connected to the sender. Switches use software on application-specific integrated circuits to make very quick decisions. A switch will use one of two methods to make forwarding decision after it receives a frame. So here we have the store and the forward switching. It receives the entire frame. After receiving all this data, the entire frame, and ensure the whole frame is valid. That requires it stores into the RAM checking and then to forward. So this is the store and the forward switching. This is the Cisco's preferred switching method. The other method is the cut-through switching. Forwards the frame immediately after determining the destination MAC address of an incoming frame and the egress port. This method is faster and requires less overhead because it uses less CPU resource. It doesn't need to process the whole frame information. For the store and the forward switching, there are two primary characteristics. Error checking. The switch will check the frame check sequence for the CRC errors. The bad frame will be discarded. So as you can see, it checks the errors. Therefore, the quality, the outcome is better, but require more CPU resource. CPU processes is slower, waste a little bit more power, and so on. Buffering. The ingress interface will buffer the frame while it checks the FCS. This also allows the switch to adjust the potential difference in speeds between the ingress and the egress ports. The cut-through forwards the frame immediately after determining the destination MAC. The frag-free method will check the destination and ensure the frame is at least 64 bytes. This will eliminate rounds. So the concept for cut-through switching is appropriate for switches needing latency to be under 10 microseconds. So 1 microsecond is 1 millionth of a second. So here we have 10 of a millionth of a second, which is pretty fast. Does not check the FCS. It can contain errors. So for a certain activity communication, having many errors is not too crucial, may use this method, the cut-through switching method. May lead to bandwidth issue if the switch propagates too many errors, cannot support ports with differing speeds going from ingress to egress.